Isolation and characterization of a natural product, caffeine. Purpose. In this experiment, the technique solid-liquid extraction and liquid-liquid extraction were used to isolate caffeine from tea leaves. Sublimation was a new technique learned that was used to purify the final product. Materials used in this experiment include the following: glassware, a 100 milliliter round bottom flask, separatory funnel, water jacket condenser, Elmer's flask, stirring rod, 12 milliliter centrifuge tube. It also included a Bunsen burner, hot plate, and vacuum. The compound of interest in this experiment was caffeine. It is not a carcinogen, however, repeated or prolonged exposure can cause organ damage. Dichloromethane was also used in this experiment. Dichloromethane is a carcinogen. It causes irritation to eye, skin, and respiratory tract. It can be harmful if swallowed. Sodium carbonate was used. It is not a carcinogen, however, it causes irritation to skin, eyes, and respiratory tract. Sodium sulfate was also used, which carcinogen effects were not available. However, it does cause irritation to eye and skin. Caffeine is commonly found in everyday products such as coffee, tea, soda, and energy drinks. What we have here on the corner is a comparison of soda to energy drinks to coffee. So if you want to feel awake and alert, coffee would be your best bet. But like I said, commonly used for alertness. However, it could also be used for painkiller, for headaches, to treat asthma, ADHD, shortness of breath on newborns, and low blood pressure. It could also be used for weight loss and type 2 diabetes. And another products that they have out is these no-dose pills, which is concentrated caffeine. It helps you stay alert and awake throughout the day, which is pretty cool. I'm going to have to try it out one of these days. Sodium carbonate was dissolved in the water used to extract the caffeine. As we see in the corner here, we have the structure of sodium carbonate, and it has negative charges on its on its oxygens, which attracted hydrogens from its surrounding environments. In this case, it was the tea leaves in the water. Sodium carbonate deprotonated caffeine and organic acids from the tea leaves. This allowed the caffeine to dissolve in dichloromethane, but not the salt. After the solution of water and sodium bicarbonate was added to the tea leaves, the complete solution was heated, which allowed the water to expand the leaves, dissolving caffeine in water along with other impurities. As we can see here, a similar setup as distillation was set up. However, the whole theory or procedure was different. Instead of collecting the distillate here in the water jacket condenser, we allowed it to recondense and to move downstream again and recollect it. We weren't purifying it or anything. We were just recollecting the vapors or the solution that was vaporizing. When liquid solid extraction was over, we moved on to liquid extraction. This two-step procedure allowed us to have a more pure sample at the end of our experiment. We took the solution from the solid liquid extraction. We filtered it out, which was a pain because the solution was thick and it clogged up the filter. However, when we got it done, we had a filtrated solution of water and caffeine, which was really thick still. However, the main point was that caffeine was removed from the leaves, and it was in an aqueous solution. We mixed it with dichloromethane, which is nonpolar, which is why they are immiscible. And we see that here, the two layers, methylene chloride at the bottom and the aqueous solution up top. And the reason one's at top and one's in the bottom is just a difference in density. Because of the sodium bicarbonate, caffeine does dissolve in dichloromethane. So what we did is we mixed the two immiscible liquids together just by moving it back and forth gently because we didn't want to create an emulsion. I did a pretty good job. I didn't get any emotions, which I got to skip a step of centrifuging. So we mixed the aqueous and dichloromethane layers together a few times, and collected the dichloromethane layer. We did this 5 times with a volume of 2 milliliters. This allowed that we get the most caffeine out of the aqueous layer. The next step was to dry and evaporate the dichloromethane in order to obtain our caffeine, our crude caffeine. Sodium sulfate was added to our dichloromethane solution, and it didn't take much to dry it. After that was done, we heated it, the dichloromethane. We filtered out the sodium sulfate, and we heated the dichloromethane. Due to its low boiling point, it was fairly easy to evaporate without damaging our caffeine. The final crude caffeine that remained was 0.04, 36 grams of it. After evaporating the dichloromethane, the crude caffeine remained on the side of the flask. This is the poor quality picture, so you're unable to see. However, it was on the side of the flask, and we did a technique called sublimation, where matter goes straight from being solid to a gas. And the way we accomplished this was through 2 conditions: high temperature and low atmospheric pressure. The way we lowered the atmospheric pressure was through a vacuum. We connected it to the flask, we sealed it up top, and turned on the vacuum. This lowered the atmospheric pressure, which allowed the sublimation of the matter to be reached. We provided a cold surface. Here you see that it's set up by water. However, what we did is we just put ice in here, which allowed it to have a cold surface to recondense, and so we heated it, it sublimated, and then it reached the cold surface, which allowed it to condense. Through this technique, the impurities are left in the flask at the bottom, and the pure caffeine it's recondensed on the surface of the tube here. The amount of crude caffeine that we started was 0.0436 grams. Purified caffeine was 0.0161 grams, which was a total of 36.93% recovery. The way we determined the purity of our caffeine was through melting point. So what we did is we packed our caffeine in one of these tubes. We sealed it because caffeine reaches its sublimation point before its melting point, and we sealed it so it won't escape as it sublimes when it heats. We placed it in the apparatus and heated it till it melted. I determined my melting point to be 210.1 Celsius. The actual melting point is 238. This means that there were some impurities, which is why it's melting at a lower temperature. Error could have occurred during the sublimation process. When we placed the ice on the centrifuge tube, water could have condensed outside the ice, and then we sublimated our sample, and when it recondensed on the wet surface, it could have gotten wet, and then melting it would have gave us a lower melting point, which would explain our decrease in temperature. Here we have our results table. The amount of tea leaves that were used was 1.66 grams. From that, we were able to retrieve 0.0436 grams of crude caffeine. From sublimation, the amount of purified caffeine retrieved was 0.0161 grams. The melting point of that was 210 degrees Celsius. Calculations were done, and was determined that for every 1 gram of those tea leaves, 0.0273 grams of crude caffeine could be extracted. Here we have an IR spectrum for caffeine. Here we have the structure, and the significant peaks that pop right out are the C double bond O, chart right here at around 17,000. And over here we have peaks at below 3,000 and above 3,000, which signifies sp3 and sp2 ch orbitals. Here we have a H and MR spectrum for caffeine. From the structure, we can see that there's 3 different H's, which we have this one here, this one here, this one here, and there's one that's not drawn in there here. That should give us 4 peaks in the H and MR spectrum, but we see that we have 1, 2, 3, 4, 5. The resource from where I got the H and MR spectrum attributed the peak to the solvent that was used to acquire the H and MR spectrum. And as we can see, the most shielded one would be the one connected to the ring, which would be here. The one that follows would be this one, because it's being deshielded by the double bond here and the double bond here. That would give us this peak here. The following peak, this one here, would be attributed to these H's here, and that is because it's closest to this double bond. The least deshielded one would be this one. It's connected to a nitrogen and there is no double bonds here. Resources were pulled from the following: WebMD, Chem 242, the Spar Hawk School PTO.